Reading math can feel daunting. Are you telling me that mathematicians looked at the simple concept of limits and decided to describe it like this? Why do we need such complicated notation to express ideas in math? Well, the main problem is that relying on informal language alone is often not precise enough. We might intuitively think of the limit of a function at a point as the value the function approaches when the input approaches the value. But with this intuition, how do we, say, show that the limit of the sum of two functions is the sum of their limits? Where do we even start? Without formal language to help us, we would be using formulas of limits without knowing for sure if they're correct, even if they seem so. With formal notation, we can make precise definitions to derive further results, which is how math advances. And in this video, I'd like to convince you that such formal notation is not as daunting as it seems, if we get to know each of the moving parts. In math, everything comes down to sentences. If we write everything down in words, sentences in math get tediously long, especially when the same quantity is referred to multiple times. This is where we'll take our first step into formal mathematical language. We can use what are called variables to represent the quantity that's being repeated. Usually, we use single letters for this. Next, we can use symbols to represent concepts that are tedious to write completely. We can use variables and symbols in any type of sentences, like questions. The point is to make sentences easier to digest. Let's see if we can rewrite this using variables and symbols. Here's another example. Using variables and symbols, we can make the sentence easier to look at. Notice that depending on what numbers we choose to replace the variables with, this sentence can be either true or false. On the other hand, our first sentence, no matter what numbers we choose, will always be true. This sentence is called a statement. A statement is a sentence that is either true or false, but not both. So we can assign one truth value to each statement. In math, working with what we know is always true or false helps us in our deductions, and this is why statements are valuable. But by introducing variables, we added a sort of generality to our sentence that makes it sometimes true and sometimes false. Let's try to change this sentence to a statement by restricting the generality. We can do this by adding conditions. For example, if x is 1 and y is 2, then x plus y is greater than 0. This is a type of statement called a conditional statement, which has the form if hypothesis, then conclusion. Now this sentence is always true. Here's another conditional statement. This sentence is always false. Also, note that the hypothesis is at the end, and we can rewrite it whichever way we like. Conditional statements tend to be more useful when the conditions are broader. For example, we can widen the scope of our conditional statement to positive numbers, and the statement still only has one truth value, which is true, but the statement says a lot more than the previous one. If we further widen this condition to any real number, the statement will then always be false. Now, this statement and our initial sentence may seem similar, but they say very different things. The statement claims that this sentence is true no matter what number we choose, whereas the sentence is a claim about some specific numbers we don't know, and hence has no truth value. It turns out that these more general conditional statements are so useful that they are actually also another type of statement called a universal statement, and can be written in this way. Let's look at what these symbols mean. This symbol means that X belongs to a set. In math, a set is any collection of objects. For example, we have the set of shapes or the set of even numbers. Sets are usually represented by a single large letter. The set of real numbers is denoted by R. So, saying that X is an element of R is the same as saying that X is a real number. And observe that we are again using the concept of variables and symbols. Now, this upside down A is a quantifier, and it simply means for all. And this statement is claiming that this is true for any real number. So, we can rewrite conditional statements as universal statements. This also works the other way around. If we have a universal statement, say, all cats are mammals, an equivalent conditional statement is, if C is a cat, then C is a mammal. Let's see if we can rewrite these statements in the other type. A universal statement makes a claim about the whole set, and if the claim is false for even one element in the set, the whole statement is false. So, we have a definite true or false value, like a conditional statement. On the other hand, there's another type of statement called an existential statement that uses this quantifier instead, which means there exists. For an existential statement, as long as the claim is true for at least one element in the set, the whole statement is true. So, if this was an existential statement instead, it will be true since we can find an example of two real numbers such that the claim is true. A universal statement and its existential counterpart are not always opposites. Here, both statements are true. So how do we find the opposite or the negation of a universal statement? A universal statement is false when there is at least one counterexample. This is actually an existential statement, where the claim is the opposite. The universal statement is saying all the circles in S are red, whereas the existential statement is saying that there is at least one non-red circle in S. It must be that one is true and the other is false, no matter what S contains. Hence, to negate a universal statement, we simply find the existential statement where the claim is negated, and we do the same thing to negate an existential statement. We can also use both quantifiers in the same statement. In this statement, this existential claim applies for each person, so it means that each person has a cat. Now, exchanging the order of universal and existential quantifiers changes the meaning of the statement. Again, this universal claim applies for at least one cat. This means that there is this one specific popular cat that is owned by everyone. Let's see if we can figure out whether these statements are true or false. Now that we are familiar with simple statements, we are ready to combine them to build compound statements. To see our compound statements more easily, let's represent the simple statements themselves as variables. There are three basic ways of creating compound statements. We've actually encountered the first, negation. This squiggly line means not, and it negates a statement. So, if P is it is raining, then not P simply means it is not raining. Just like the truth and falsity of sentences depend on the value of the variables, the truth value of compound statements depend on the truth values of the statement variables that they are made up of. To keep track of all the possible truth values in the compound statement, we can list them in the truth table. First, let's write down the possible truth values of the simple statement: true and false. Now, if P is true, then not P should be false, and if P is false, then not P is true. While the truth table may not seem very useful right now, it is going to be much more helpful as we get to more complicated compound statements. The second way of creating compound statements is through conjunction. This upward pointing symbol means and the compound statement is only true when both statement variables are true. In our truth table, we list down each combination of truth values for the simple statements. The compound statement is only true when both simple statements are true, so we write false for every other row. In logic, negation is performed before conjunction. This rule avoids the ambiguity we face in everyday language. For example, when we say I'm not sad and angry, do we mean I'm not sad and I'm angry, or I'm not sad and I'm not angry? If we use compound statements instead, we get rid of any ambiguity. Another source of imprecision is that different words in everyday language can have the same logical meaning. For example, besides and, but can also be used for conjunction since it connects two separate statements together. The distinction between and but in everyday language is that but connects two statements that we don't expect to be connected. But in math, we're not really concerned about what we expect. Let's take a look at another example. Another way of saying not P and not Q in everyday language is neither P nor Q. For example, saying I'm neither happy nor sad is equivalent to saying I'm not happy and I'm not sad. Let's try filling out the truth table for this compound statement. Starting with the simple statements and their possible truth values, we proceed with the next simplest compound statements, not P and not Q, in their own columns. Next, we simply apply conjunction to these two columns. This truth table supports our intuition that the statement must only be true if both simple statements are false. The third way of creating compound statements is by disjunction. This downward pointing arrow means or, and this compound statement is only false if both statements are false and is true otherwise. Hence, we'll put false in the last row and true for every other row. Let's try to form a more complicated compound statement. In our current definition of or, the statement is true when both simple statements are true. What if we wanted an exclusive or that's only true when only one of the simple statements are true, and false if both or neither of them are true? Let's start with everyday language. By exclusive or, we mean P or Q, but not both. We discussed how but is also a conjunction, and both can be represented as a conjunction of P and Q. Outside this conjunction, we have a negation. So, this represents the exclusive or of P and Q. Let's see if we can construct the truth table for this statement. Again, from the simple statements, we'll start with the smallest compound statements first. The next step is this negation. Then, our final step is a conjunction of these two. This truth table supports our intuition of what exclusive or means. Now, how do we negate conjunctions and disjunctions? If we have a statement with a conjunction, for example, Jim is tall and he is blonde, either one of the statements needs to be false for this whole statement to be false. Hence, the negation of the statement is Jim is not tall or he is not blonde. To negate a conjunction, we negate the individual statements and put them in a disjunction. We can say that these two statements are logically equivalent. Two statements are logically equivalent if they always have the same truth value, regardless of the truth values of the simple statements. In other words, they have the same truth value for every row in the truth table. Let's see if you can check whether this is the negation of a disjunction using a truth table. These two logical equivalences, the negation of conjunctions and disjunctions, are called de Morgan's laws. Now look at this statement. This statement might seem redundant, and that's because it's always true. When we put a statement and its negation in the disjunction, the whole statement must be true because one of the statements is true. In the truth table, all the rows for the statement are true. A statement that is always true is called a tautology. On the other hand, if we put a statement and its negation in a conjunction, the whole statement must always be false, since one of the statements is false. A statement that is always false is called a contradiction. Needless to say, all tautologies are logically equivalent to one another, and all contradictions are logically equivalent to one another. Sometimes, to prove a statement, mathematicians take the negation of the statement and derive logically equivalent statements until they reach a very obvious contradiction. This means that the negated statement itself is a contradiction, and so the original statement must be a tautology. There are 10 common laws for logical equivalences that you can verify using truth tables. Using these laws helps us show a lot of other logical equivalences more easily. For example, using the associative law, which says that we can group the variables either way if the logical connector is the same, we can easily deduce this logical equivalence, which would have required a truth table with 16 rows. Though, we do need a truth table to show that two statements are not logically equivalent, by finding at least one different row. There's actually one more way of creating a compound statement, using conditional statements. Instead of seeing the hypothesis as a restriction to the second statement, we can see it as a statement itself. The statement if P then Q can be written with an arrow from P to Q. Now, the thing is that P and Q don't need to be related. We only care about whether the truth value of Q follows the truth value of P. As long as Q is true when P is true, the whole statement is true. For example, this statement is false since Q is false when P is true. On the contrary, the statement if today is rainy, it is sunny is true if both statements happen to be true for today, even if the conclusion itself doesn't depend on the hypothesis. We know what happens when the hypothesis is true, but what if it's false? Suppose a mom tells her child, if you score well in this exam, I'll give you a candy. If the child then fails the exam, the mom wouldn't have broken the promise regardless of whether she ends up giving him the candy or not, since she didn't say anything for the case of the child not doing well for the exam. The promise is only broken if the child does well in the exam and the mom doesn't give him candy. Hence, we consider the statement to be true by default or vacuously true when the hypothesis is false. Thus, the truth values of the conditional statement can be summarized in this way. Hence, the statement if all dogs have 3 legs, cats lay eggs is strangely true. Let's try to construct a truth table for this statement. Starting with the simple statements, we continue with the disjunction of P and Q. By the associative law, these statements are equivalent, so we can proceed with the disjunction of P or Q and R. Then, let's fill in the column for P and Q. Now, this is the hypothesis and this is the conclusion. So, the final statement is only false if we see it true for the hypothesis and false for the conclusion. Now, can you show that these statements are logically equivalent using a truth table? In fact, this is called the contrapositive of a conditional statement, and it's an important fact that the conditional statement is logically equivalent to its contrapositive. For example, the statement if it rains, I'll bring an umbrella is equivalent to if I don't bring an umbrella, it wouldn't have been raining, since these two statements are only false when it rains but I don't bring an umbrella. Let's take a closer look at this statement. The only case where I won't be bringing an umbrella is if it doesn't rain. Hence, an equivalent statement is I don't bring an umbrella only if it won't be raining. So, we see that these two statements are equivalent. In general, if we replace the arrow in the conditional statement with only if, we get an equivalent statement. We say that P is a sufficient condition for Q, since by having P be true, Q can be true, but Q may also be true when P isn't. On the other hand, Q is a necessary condition for P, since Q must be true for P to be true. When P is a sufficient condition for Q, it immediately holds that Q is a necessary condition for P. If both of these statements are true, then we say that P and Q are necessary and sufficient conditions for each other. This means that when P is true, Q must be true, but if P is false, then Q is false. This means that P and Q are logically equivalent to each other, and we call this a biconditional statement. In a biconditional statement, each statement leads to the other, and we usually say P if and only if Q. The if part says that Q is a sufficient condition for P, whereas the only if says that Q is a necessary condition for P. This statement is most often used for definitions, since definitions are nothing more than logical equivalences. For example, we can say an integer is even if and only if it is 2 times some integer. Let's use everything we learned to understand the formal definition of a limit. Remember, our intuition was that the limit of fx at x equals to a being L means that fx approaches L as x approaches a. Since this is a definition, we can use a conditional statement. Now consider drawing a box centered at a point AL. Start by taking some horizontal distance from the point. This will determine the horizontal sides of the box. Then, at the points where the line intersect the curve, choose the one vertically further from A, and we have a box centered at AL. Notice that if x is within this distance from A, then fx must be within this distance from L. This is a conditional statement. We can represent the distance between two numbers as the absolute value of their difference, and use the concept of variables to represent the horizontal and vertical distances, delta and epsilon. What makes the limit so special is that no matter how small the height of the box is, we can always find one such box that contains the point AL, along with all the other points of the curve in this region. Consider another point that isn't the limit. While we can find some boxes, we can set the height small enough such that no box can contain both the point and the other points of the curve in the horizontal range. So, for L to be the limit, for any vertical distance from L, there's a horizontal distance from A that creates this box, such that this is true. This definition encapsulates pieces of our intuition into a precise statement. The existential statement describes the existence of a box. The symbols represent the size of the box. The universal statement says that this box can be of any height. And the conditional statement says that this box contains the horizontal portion of the curve. As with anything else, mastering formal mathematics comes with practice. This video was inspired by the first 3 chapters of Susanna App's Discrete Math textbook. And if you're interested, I'd highly recommend going over these chapters and solving the exercises to gain a deeper appreciation of what this video covers. Familiarizing yourself with writing math precisely opens doors to many exciting branches of upper-level math. Anyway, I hope you enjoyed this video, and I'll see you in the next one.